Every plan to send humans to Mars obsesses over the same question. How do we get there alive? Billions of dollars pour into heat shields, radiation shielding, landing systems, and surface habitats. But NASA engineers lose sleep over a completely different problem, one that almost nobody talks about. The real danger is not landing on Mars, it is leaving. Once astronauts touch down on that rust-coloured desert, they face a terrifying truth. There is no launch pad. There is no mission control standing by with a backup rocket. There is no rescue ship in orbit. The only way home is a small, unproven vehicle that must manufacture its own fuel from the Martian atmosphere, launch from an alien world, and dock with a waiting spacecraft before a narrow window slams shut forever. If you want to understand the part of Mars exploration that keeps rocket scientists awake at night, hit that like button and subscribe. Now, get yourself nice and comfortable. Let's begin. Every documentary you have watched about Mars follows the same storyline. The rocket launches from Earth in a tower of fire. The spacecraft crosses tens of millions of miles of interplanetary void. Then comes the dramatic entry, the heat shield glowing white hot, the parachute deploying in thin air, the retro rockets firing in the final seconds before touchdown. The cameras cut to mission control. People cheer, tears flow. Humanity has arrived on another planet. It is a beautiful story. It is also dangerously incomplete. The narrative of Mars exploration as told to the public focuses almost entirely on one direction: outbound, getting there. The assumption buried inside that framing is subtle but enormous, that if you can land on Mars, you have essentially solved the problem. The rest is just details. Surface operations, science, maybe growing some potatoes. The return trip is treated as an afterthought, a mirror image of the outbound journey, something that will sort itself out once the hard part is done. NASA engineers know this is backwards. The hard part is not getting to Mars. The technology for interplanetary transit exists today, proven through decades of robotic missions. The Curiosity rover landed in 2012, using a sky crane system so audacious it seemed fictional. The Perseverance rover repeated the feat in 2021 with even greater precision. We know how to cross interplanetary space. We know how to survive the entry. We know, within reasonable engineering margins, how to land heavy payloads on the Martian surface. What we do not know how to do, what no space agency on Earth has ever demonstrated with human-rated hardware, is get off Mars and come home. This is the problem that defines everything. The Mars Ascent Vehicle, sometimes called the MAV, is the single most critical piece of technology in any crewed Mars mission architecture. It is also the least tested, the most constrained, and the most unforgiving. Every other component of a Mars mission has analogues in existing spaceflight. We have launched humans from Earth thousands of times. We have kept crews alive in space for over a year aboard the International Space Station. We have landed robots on Mars repeatedly. But launching humans off the surface of another planet and returning them to Earth, that has never been done. Not once. Not even close. The Apollo missions provide the nearest comparison, and the comparison reveals how much harder Mars will be. When Apollo astronauts launched off the Moon, they used an ascent stage that carried its own fuel from Earth. The lunar module's ascent engine burned hypergolic propellants, chemicals that ignite on contact, requiring no ignition system that could fail. The Moon has no atmosphere, so there was no aerodynamic drag to fight. The command module waited in lunar orbit just 60 miles above the surface. The entire rendezvous could be completed in a matter of hours. And even with all these advantages, the ascent off the Moon was considered the most dangerous phase of each Apollo mission. Gene Kranz, the flight director for Apollo 13, later described the lunar ascent engine as the component that frightened him most. If it did not light, the astronauts died on the Moon. There was no plan B. Now multiply every one of those challenges by an order of magnitude. Mars has gravity. Not as much as Earth, roughly 38%, but dramatically more than the Moon's 16%. A vehicle launching from Mars must fight real gravitational pull, not the gentle tug that lunar ascent stages overcame. On the Moon, the ascent stage needed to achieve a velocity of roughly 1.7 kilometers per second to reach lunar orbit. On Mars, the required velocity is closer to 3.5 to 4 kilometers per second. That difference sounds modest expressed in numbers. Translated into propellant mass, it is devastating. The relationship between velocity and fuel is not linear. It is exponential. Doubling the required velocity does not double the fuel, it can increase it by a factor of 5 or more, depending on the engine's efficiency. Mars demands more than twice the velocity change of a lunar ascent, and the fuel penalty multiplies through the rocket equation into a problem that reshapes the entire mission. Mars has an atmosphere. This sounds like it might help. Perhaps the vehicle could use aerodynamic lift during ascent, the way aircraft do on Earth. It does not help. The Martian atmosphere is roughly 1% the density of Earth's atmosphere at sea level. 1%. That is thick enough to create significant aerodynamic drag during ascent, forcing the vehicle to push through resisting air that slows it down and requires additional fuel to overcome. But it is far too thin to generate meaningful lift or allow aerodynamic control surfaces to function with any authority. The atmosphere imposes penalties without offering benefits. It is the worst of both worlds. To put that atmospheric density in perspective, consider what 1% of Earth's atmosphere actually means. At sea level on Earth, the atmospheric pressure is approximately 1,013 millibars. On the surface of Mars, the average pressure is roughly 6 millibars. That is less than the pressure at the summit of Mount Everest. It is less than the pressure at the altitude where commercial aircraft cruise. A human standing on the Martian surface without a pressure suit would experience something close to explosive decompression. The air is there, you can see its effects in dust devils and cloud formations, but it is so thin that it exists in a strange middle ground between vacuum and atmosphere. Too much to ignore during a rocket launch, too little to exploit. The distances involved compound the difficulty. The Earth return vehicle will orbit Mars at an altitude of several hundred kilometers. The ascent vehicle must reach that altitude, match the orbital velocity of the waiting spacecraft, and execute a rendezvous and docking sequence, all while operating on a world where the speed of light creates a communication delay of between 4 and 24 minutes, depending on planetary alignment. When Mars is on the near side of its orbit relative to Earth, signals take about 4 minutes each way. When both planets are on opposite sides of the Sun, the delay stretches to over 20 minutes. In either case, ground controllers on Earth cannot fly this in real time. A command sent from Houston takes minutes to reach Mars. The vehicle's response takes minutes to travel back. By the time controllers see what happened, the moment has long passed. The vehicle must either operate autonomously or be piloted by the crew with minimal external support. Compare this to how rendezvous works in Earth orbit. When a Soyuz capsule approaches the International Space Station, ground controllers monitor the approach in near real time, with communication delays measured in milliseconds. Radar tracking stations around the world continuously update the vehicle's positions. If something goes wrong, controllers can intervene within seconds. For Mars, that entire support infrastructure is replaced by silence. The crew is alone. And here is the factor that changes the entire equation. The ascent vehicle cannot carry all its fuel from Earth. This is worth pausing on, because it represents the single most consequential constraint in all of Mars mission planning. On every previous human spaceflight mission in history, the propellant needed for every maneuver was loaded into the vehicle before it left the ground. The Saturn V carried its fuel. The Space Shuttle carried its fuel. The Soyuz carries its fuel. Even the Apollo lunar module carried its ascent fuel from Earth, across 240,000 miles of space, all the way to the lunar surface. For Mars, this approach is physically impossible. The reason is the tyranny of the rocket equation, formulated by Konstantin Tsiolkovsky in 1897, and just as merciless today as it was then. The equation describes a brutal exponential relationship between the mass of fuel required and the velocity change a rocket must achieve. Every kilogram of payload you want to bring home from Mars requires multiple kilograms of fuel, but that fuel itself has mass, which requires more fuel to lift, which requires more fuel to carry, and so on. The numbers spiral upward with terrifying speed. The mathematics work like this. Suppose your ascent vehicle has a dry mass, the vehicle without fuel of 5 tons. To achieve the velocity change needed to reach Mars orbit, you might need 10 tons of propellant, depending on the engine's specific impulse. So your vehicle at launch weighs 15 tons. But you had to land that 15-ton vehicle on Mars, and landing it required fuel. The landing fuel adds mass to the vehicle entering Mars's atmosphere, which means you needed more fuel to decelerate from interplanetary speed. That deceleration fuel adds mass to the spacecraft leaving Earth orbit, which means you needed more fuel for the trans-Mars injection burn. And that fuel adds mass to the rocket sitting on the launch pad at Cape Canaveral. Every kilogram of ascent propellant you want on the Martian surface translates to dozens, in some estimates, hundreds of kilograms on the launch pad on Earth. The cascade is relentless. To carry enough preloaded fuel for a round trip to Mars and back, you would need a spacecraft so massive that no existing or planned rocket could launch it. Some estimates place the total mass at well over 1,000 tons in low Earth orbit, roughly 7 times the mass of the International Space Station. Even the most optimistic projections for SpaceX's Starship system, which aims for a payload capacity of around 100 to 150 tons to low Earth orbit, would require an absurd number of launches and orbital refueling operations just to assemble the outbound stack. And that is before accounting for the fuel needed to land that fuel on Mars, which requires even more fuel, which requires a larger landing vehicle, which requires more fuel to get to Mars in the first place. The rocket equation does not negotiate. So mission architects arrived at the only workable solution. Do not bring the return fuel, make it there. This is in situ resource utilization, ISRU, and it represents the most radical departure from traditional spaceflight philosophy ever seriously proposed for a crewed mission. The idea is elegant in concept. Mars has an atmosphere composed of roughly 95% carbon dioxide. If you can process that carbon dioxide with hydrogen brought from Earth, you can produce methane and oxygen through a well-understood chemical process called the Sabatier reaction. Methane and liquid oxygen happen to be excellent rocket propellants, the same combination that powers SpaceX's Raptor engines. The concept works in laboratory conditions. NASA's MOXIE experiment aboard the Perseverance rover demonstrated oxygen production from Martian carbon dioxide in 2021, producing roughly 6 grams of oxygen per hour. The experiment ran 16 times over approximately 2 years, producing a total of roughly 122 grams of oxygen. NASA declared it a success, and it was as a proof of concept. As a stepping stone toward keeping humans alive on another planet, it demonstrated that the basic chemistry functions on Mars. But a human return mission would require producing somewhere between 20 and 30 tons of propellant. The gap between 122 grams and 30 tons is not a gap, it is a chasm. It is the difference between boiling a cup of water in your kitchen and supplying a city's water treatment plant. The chemistry is the same. The engineering is separated by orders of magnitude, but none of this matters if the ascent vehicle does not start. That sentence deserves to sit with you for a moment, because it is the gravitational center of this entire story. Every innovation in Mars habitat design, every advancement in radiation shielding, every breakthrough in growing food on alien soil, all of it becomes meaningless if the crew cannot leave. You can build the most sophisticated Mars base in human history, equip it with every tool science can provide, and keep a crew healthy and productive for 500 days on the surface. And if the ascent vehicle fails, that base becomes a monument, because nobody is coming to get them. This is not dramatic license. This is engineering reality. A rescue mission to Mars does not exist in any meaningful sense. If a crew is stranded on the surface, the earliest another vehicle could reach them, assuming one was already built, fueled, and sitting on a launch pad on Earth, would be roughly 2 years. That is the minimum time required for Earth and Mars to realign for another transfer window. But 2 years is the optimistic figure. It assumes a rescue vehicle is ready to launch the moment the distress call arrives. In reality, no such vehicle would be standing by. Designing, building, testing, and launching a rescue mission would take years, even under crash program urgency. By then, the surface habitat's consumables, its food stores, its water recycling capacity, its carbon dioxide scrubber cartridges, its oxygen supply would have long been exhausted. The International Space Station can be resupplied within days by multiple vehicles from multiple nations. A crew in low Earth orbit can return home within hours using a Soyuz capsule. Even the Apollo astronauts, at their most distant, were only 3 days from Earth. If something went wrong, and something did go wrong on Apollo 13, there was a realistic prospect of getting the crew home alive. A Mars crew is months from home under the best of circumstances. Under the worst, they are simply gone. Let me walk through the full mission sequence to show you exactly where this bottleneck sits and why it dominates every other consideration. Phase 1 is Earth departure. The crew launches from Earth during a transfer window that opens roughly every 26 months when the 2 planets align favourably. This window is not optional, and it is not flexible. Miss it, and the crew waits over 2 years for the next one. The outbound transit takes between 6 and 9 months depending on the trajectory chosen. During this transit, the crew lives in a deep space habitat, exposed to solar and galactic cosmic radiation, experiencing microgravity that weakens bones and muscles, and travelling farther from Earth with every passing hour. It is grueling, but it is understood. Humans have lived in space for comparable durations aboard the International Space Station. Phase 2 is Mars arrival and landing. The spacecraft enters Mars orbit, and the crew descends to the surface in a landing vehicle. This is the famous 7 minutes of terror, the entry, descent, and landing sequence that must decelerate the vehicle from interplanetary speed to a safe touchdown. It is genuinely dangerous. The thin Martian atmosphere creates a narrow corridor of feasibility. Enter too steeply and the deceleration forces destroy the vehicle. Enter too shallowly and the vehicle skips off the atmosphere back into space. Even with a perfect entry angle, the vehicle must deploy supersonic parachutes, fire retro-rockets, and execute a precision landing, all autonomously, because the communication delay makes real-time control impossible. It is dangerous, but it has been done successfully with robotic payloads multiple times. The landing sequence is a solved problem in principle, if not yet at the scale required for human missions. Phase 3 is the surface stay. Current mission architectures envision a surface stay of roughly 500 days. This is not an arbitrary number. It is dictated by orbital mechanics. After arriving on Mars, the crew must wait for Earth and Mars to move into position for a favourable return trajectory. The planets are in constant motion, orbiting the Sun at different speeds and different distances. Mars completes one orbit every 687 Earth days. Earth orbits every 365. The 2 planets align for efficient transfers only at specific intervals. During the 500-day surface stay, the crew conducts science, maintains the habitat, and critically monitors the fuel production system that will determine whether they can leave. Phase 4 is Ascent. The crew boards the Mars Ascent Vehicle and launches from the surface to Mars orbit. This is the phase that has never been attempted, never been tested with human-rated hardware, and offers zero margin for failure. No abort mode, no backup vehicle, no emergency landing site. The engine either fires and performs correctly or it does not. Phase 5 is orbital rendezvous and docking. The Ascent Vehicle must locate, approach, and dock with the Earth return vehicle waiting in orbit. This must happen within a specific window dictated by the return trajectory timing and the limited fuel the Ascent Vehicle carries. Unlike rendezvous in Earth orbit, where multiple attempts can be made over successive orbits, the Mars rendezvous offers very few chances. The Ascent Vehicle carries limited propellant for orbital maneuvers. Each failed attempt consumes fuel that cannot be replaced. Phase 6 is the trans-Earth injection burn. The combined vehicle fires its engines to leave Mars' orbit and enter a transfer trajectory toward Earth. This burn must occur at the precise moment when Mars's orbital position allows a trajectory that intersects Earth's orbit 6 to 9 months later. The timing is constrained by celestial mechanics. The margin is measured in days, not weeks. Phase 7 is Earth arrival. The crew separates from the transit vehicle, re-enters Earth's atmosphere in a capsule, and lands. This phase uses technology derived from existing capsule re-entry systems and, while still dangerous, represents the most mature segment of the entire mission profile. Look at that sequence carefully. Phases 1, 2, 3, and 7 all have precedent. Not identical precedent, landing humans on Mars will be far harder than landing robots, but the fundamental physics and engineering have been demonstrated in some form. Phases 4, 5, and 6 have no precedent at all for a crewed mission at Mars. Zero. None. These 3 phases represent the return problem, and together they form the most complex chain of dependent events ever proposed in human spaceflight. Each phase depends absolutely on the one before it. You cannot dock with the return vehicle if you did not reach orbit. You cannot reach orbit if the ascent engine did not fire. The ascent engine cannot fire if the fuel was not produced. The fuel cannot be produced if the ISRU system did not function. Every link in this chain must hold, and there is no workaround if any single link breaks. The Martian atmosphere compounds the difficulty of ascent in ways we will examine in detail later. For now, the essential point is this: the vehicle must fight through air that slows it down without providing any of the aerodynamic control that Earth launches rely on. Every aspect of steering falls to the engines alone. Wind adds another variable. Martian dust storms can produce winds exceeding 100 kilometers per hour, and while the thin atmosphere means these winds carry far less kinetic energy than on Earth, they still matter during those first critical seconds when the vehicle is moving slowly and most vulnerable to being pushed off course. On Earth, launches are routinely scrubbed for weather. On Mars, the departure window dictates the schedule, and the window does not care about dust storms. And then there is the dust itself. Mars is covered in fine iron oxide particles, rust, essentially with a grain size measured in micrometers, finer than talcum powder. This dust gets everywhere. It coats solar panels, reducing power output. It clogs filters, degrading air processing systems. It adheres to every surface through electrostatic charge, building up in layers that resist removal. The Viking landers observed dust accumulation in the 1970s. The Spirit and Opportunity rovers battled it for years. The InSight lander was effectively killed by it in 2022, when dust accumulation reduced its solar panel output below the threshold needed to operate. Over a 500-day surface stay, Martian dust will inevitably infiltrate the ascent vehicle's systems despite protective covers, sealed compartments, and every mitigation strategy engineers can devise. Every valve, every seal, every electrical connector, every sensor in the MAV must function perfectly after sitting on the Martian surface for well over a year, exposed to temperature swings ranging from minus 130 degrees Celsius at night to a relatively mild 20 degrees Celsius during the day at equatorial latitudes. That is a thermal range of 150 degrees, cycling daily, stressing materials, expanding and contracting joints, fatiguing every component through hundreds of repetitions. Everything depends on that launch off Mars. The ascent vehicle must survive the Martian environment for the duration of the surface stay, maintain the integrity of its propellant tanks, keep its engine components free of contamination, and then perform flawlessly on the first and only attempt. There is no second chance, no backup vehicle, no rescue from orbit. It is the crew, the vehicle, and the Martian sky. That is all. The public story of Mars is about the thrill of arrival, the first footprint, the first flag, the first words spoken on another planet. These are the images that inspire funding, attract talent, and capture the public imagination, and they deserve celebration. Getting to Mars will be a monumental achievement. But the real story, the one that engineers tell each other in conference rooms and late-night design reviews, the one scratched on whiteboards in buildings at the Jet Propulsion Laboratory and the Johnson Space Center, is about departure. It is about whether the crew that lands can also leave, whether the vehicle that must work will work, whether the fuel that must be made will be made, whether the chain of events that must unfold without a single failure will actually hold. Because arrival without departure is not a mission, it is a one-way trip. And building the machine that prevents that outcome, the machine that brings them home, is where this story truly begins. There is a thought experiment that crystallizes why the Mars return problem is unlike anything in the history of human exploration. Imagine you're about to climb the tallest mountain on Earth. You have trained for years. Your equipment is the finest ever made. Your support team is world-class. But there is a condition. The oxygen you will need to descend from the summit cannot be carried with you. Instead, a machine was sent to the summit 2 years before your climb. It has been running autonomously ever since, slowly extracting oxygen from the thin mountain air, compressing it, and storing it in tanks that will be waiting for you at the top. If the machine worked, you descend safely. If it failed at any point during those 2 years, a cracked pipe, a frozen valve, a power interruption, you reach the summit and discover there is no oxygen for the trip down. You are standing on top of the world with no way to get home. That is the ISRU problem on Mars. Except the mountain is another planet, the machine must work for roughly 26 months unattended. And the oxygen is not just for breathing, it is rocket propellant. Without it, there is no launch. Without a launch, there is no return. In situ resource utilization is not a nice-to-have technology for Mars missions. It is not an add-on, not an upgrade, not a feature that improves efficiency while remaining optional. It is the architecture. Remove ISRU, and you remove the return trip entirely. No serious Mars mission plan from any space agency or private company proposes carrying all the return fuel from Earth. Part 1 explained why the rocket equation makes it physically impossible without a vehicle so massive it could never be assembled, launched, or landed. The fuel must be manufactured on Mars from Martian resources, and the crew's lives depend on that manufacturing process succeeding. The chemistry itself is well understood. The Sabatier reaction, discovered by French chemists Paul Sabatier and Jean-Baptiste Senderens in 1897, combines carbon dioxide with hydrogen in the presence of a nickel catalyst at temperatures between 300 and 400 degrees Celsius. The products are methane and water. The reaction is exothermic, meaning it releases heat, which is thermodynamically favourable the reaction wants to happen. Given the right conditions, it proceeds readily and produces consistent yields. In a laboratory on Earth, it works reliably and predictably. Chemical engineers have been running Sabatier reactors in industrial settings for over a century. The reaction is used in submarine atmosphere scrubbing systems, in industrial hydrogen purification, and in experimental carbon capture processes. There is nothing exotic about the chemistry. Mars provides the carbon dioxide. The Martian atmosphere, thin as it is, consists of approximately 95.3% carbon dioxide, with the remainder being mostly nitrogen and argon with trace amounts of oxygen, carbon monoxide, and water vapor. An ISRU system would intake this atmospheric gas through a compressor, filter out the ever-present dust particles, and feed the cleaned carbon dioxide into the Sabatier reactor. The process requires hydrogen as a reactant. In baseline mission designs, this hydrogen must be brought from Earth, stored either as liquid hydrogen at -253 degrees Celsius, or chemically bound in a more stable form such as water or a metal hydride that can release hydrogen when heated. Transporting hydrogen from Earth represents a significant mass penalty, but it is far less punishing than carrying finished propellant. You are shipping a raw ingredient rather than the final product. The mass savings are substantial enough to make the mission architecturally feasible. Some advanced ISRU concepts propose eliminating even this Earth-supplied hydrogen. Mars harbours vast deposits of subsurface water ice, confirmed by orbital radar instruments aboard the Mars Reconnaissance Orbiter and directly observed by the Phoenix lander in 2008. If this ice could be excavated, melted, and electrolyzed into hydrogen and oxygen, the entire propellant production chain could run on purely Martian resources. The mission would need to bring only the processing equipment, not the feedstock. This is an appealing vision. It is also an unproven one. Mining ice on Mars requires knowing its exact location, depth, and purity at the landing site. It requires excavation equipment that can operate in Martian gravity and temperature extremes. It requires heating and purification systems to convert dirty ice likely mixed with Martian regolith and perchlorates into clean water suitable for electrolysis. Each additional process in the chain adds another potential failure point. For near-term mission planning, most architectures assume Earth-supplied hydrogen as the safer option, accepting the mass cost in exchange for reduced complexity. The Sabatier reaction produces methane and water. The methane is the fuel component of the propellant pair. To complete the combination, you also need an oxidizer, liquid oxygen. This can be produced through electrolysis of the water generated by the Sabatier reaction itself, splitting water molecules into hydrogen and oxygen using electrical current. The hydrogen liberated by electrolysis can then be recycled back into the Sabatier reactor, creating a partially closed loop that reduces the total amount of hydrogen that must be brought from Earth. Alternatively, liquid oxygen can be produced through direct electrolysis of carbon dioxide, the approach demonstrated by NASA's MOXIE experiment aboard the Perseverance rover. MOXIE used solid oxide electrolysis cells operating at temperatures around 800 degrees Celsius to split carbon dioxide molecules into oxygen and carbon monoxide. The oxygen was collected and measured. The carbon monoxide was vented into the Martian atmosphere as waste. MOXIE ran 16 times between 2021 and 2023, operating for a total of roughly 100 hours. During its operational runs, it produced between 6 and 10 grams of oxygen per hour, with its peak production reaching approximately 12 grams per hour under optimal conditions. Over its entire operational lifetime, MOXIE generated roughly 122 grams of oxygen, about what a small dog breathes in 10 hours or roughly what a single astronaut would consume, breathing normally for 5 to 6 hours. NASA declared the experiment a success, and by the standards of technology demonstration, it was. MOXIE proved that the electrochemical process works on Mars, in Martian atmospheric conditions, with Martian carbon dioxide. That confirmation was genuinely valuable, but here is where the scale problem becomes visceral. A crewed Mars return mission using methane and liquid oxygen propellant requires approximately 20 to 30 metric tons of propellant. Some estimates run higher depending on the mass of the ascent vehicle and the delta V required to reach Mars orbit. Let us use a conservative figure of 25 metric tons. Of that, roughly 75 to 80% would be liquid oxygen, reflecting the stoichiometric ratio of the methane-oxygen combustion reaction. That means roughly 18 to 20 tons of liquid oxygen and 5 to 7 tons of liquid methane. MOXIE produced 122 grams total over 2 years. The required oxygen production for a crewed mission exceeds MOXIE's total lifetime output by a factor of approximately 160,000. This is not a matter of building a slightly bigger version of the same experiment. It is a matter of scaling an experimental device by 5 orders of magnitude, while simultaneously requiring it to operate autonomously, continuously, and without maintenance for years on the surface of another planet. A full-scale propellant production plant would be a major industrial installation. Current estimates suggest it would weigh between 1 and 2 tons for the processing equipment alone, before accounting for the power system, the hydrogen storage, the propellant tanks, the thermal management hardware, and the structural support. The complete ISRU package, ready for deployment on Mars, would likely mass between 4 and 8 tons, a significant fraction of the total payload capacity for a Mars landing vehicle. It would require between 25 and 40 kilowatts of continuous electrical power. That is roughly the power consumption of 10 average American homes running simultaneously around the clock every single day for over 2 years. On Mars, where the nearest power plant is on another planet, the power source is itself a critical engineering challenge that branches into a separate tree of dependencies. 2 primary options exist, each with significant drawbacks. Solar power is the most straightforward approach. Photovoltaic panels convert sunlight to electricity, and the technology is well proven in space applications. But Mars receives only about 43% of the solar energy that reaches Earth, owing to its greater distance from the Sun, approximately 140 million miles compared to Earth's 93 million. That immediately cuts the available power nearly in half. Then factor in atmospheric absorption and scattering, which further reduce the energy reaching the surface. Then factor in dust. The Martian dust problem is not hypothetical. It is documented, measured, and relentless. The InSight lander watched its solar panel output decline from roughly 600 watts at landing to less than 300 watts over the course of 2 years as dust accumulated on its arrays. Spirit and Opportunity experienced similar degradation, though Opportunity benefited from occasional wind events that partially cleaned its panels. No reliable mechanism exists for cleaning solar panels on Mars at industrial scale. An ISRU plant that depends on solar power must either oversize its arrays to account for degradation, incorporate mechanical cleaning systems, which themselves require power, and introduce moving parts that can fail or accept declining output over time, and build production margin into the schedule. Dust storms pose an even more acute threat. Mars experiences regional dust storms that can last for weeks, reducing solar insolation to a fraction of normal. Roughly every 3 Mars years, about 5.5 Earth years, a global dust storm can encircle the entire planet, reducing surface solar energy by up to 99% for weeks or even months. The 2018 global dust storm effectively ended the Opportunity rover mission by denying it the power needed to maintain thermal control of its electronics. An ISRU system relying solely on solar power would essentially shut down during a major storm, losing weeks or months of production time that may not be recoverable within the mission schedule. Nuclear power avoids most of these problems. A small fission reactor operates regardless of sunlight, dust, storms, or time of day. It provides steady, predictable power output that does not degrade with dust accumulation or seasonal changes. NASA's Kilopower project, tested in 2018 at the Nevada National Security Site, demonstrated a prototype fission reactor using a uranium-235 core capable of producing up to 10 kilowatts of electrical power. The reactor used Stirling engines to convert heat to electricity and operated continuously for 28 hours during its final test, a brief but encouraging demonstration. However, no nuclear reactor has ever operated on the surface of another planet. The Curiosity and Perseverance rovers use radioisotope thermoelectric generators (RTGs), which produce heat from the natural decay of plutonium-238. But RTGs are not reactors. They produce modest power, roughly 110 watts, through passive radioactive decay, not through controlled fission. A fission reactor is a fundamentally different system with a controlled chain reaction, moving parts in the power conversion system, and thermal management requirements that must function in the Martian environment. Deploying one on Mars would require autonomous startup and operation, active cooling systems, and radiation shielding to protect nearby equipment and crew. The regulatory and political challenges of launching fissile material from Earth add another layer of complexity. It can be done. RTGs have flown on dozens of missions, but scaling up to a fission reactor is an undertaking that no space agency has yet attempted for a planetary surface application. The timeline is what makes all of this terrifying. In most mission architectures, the ISRU system and its power source must be delivered to Mars and begin operating long before the crew launches from Earth. The typical sequence unfolds across years. First, a cargo mission launches from Earth during one transfer window. This mission carries the ISRU plant, the ascent vehicle, the power system, the propellant storage tanks, and bulk supplies that will be needed for the surface stay. The cargo ship crosses interplanetary space for roughly 9 months and lands on Mars robotically, using an automated entry, descent, and landing system. Once safely on the surface, the ISRU system activates and begins producing propellant without human supervision. 26 months later, the next transfer window, the crew launches from Earth. They spend 6 to 9 months in transit. By the time the crew touches down on Mars, the ISRU system has been operating for approximately 2.5 years. During those 2.5 years, the system must have produced and stored enough propellant for the return trip. The crew will verify propellant quantity and quality after landing, but the fundamental commitment has already been made. They are already on Mars. The decision point was not the landing. It was the launch from Earth, when the crew committed to a destination knowing their ride home was being built by a robot on the other end. Think about what that means for mission planning. The go or no-go decision on crew launch depends on telemetry from a chemical plant operating on another planet. Mission controllers must evaluate, months before the crew departs Earth, whether the ISRU system is performing well enough to guarantee sufficient propellant by the time the crew needs to leave Mars roughly 3.5 years into the future. That projection involves forecasting the performance of mechanical and chemical systems over timescales that exceed any autonomous operational record for planetary surface hardware. The longest operating surface mission in history is the Curiosity rover, which has functioned on Mars since 2012. But Curiosity is a mobile science laboratory, not an industrial plant. It does not run high-temperature chemical reactors. It does not compress and liquefy gases. It does not store cryogenic fluids. The operational demands on an ISRU system are qualitatively different from anything that has operated on Mars to date. If the ISRU system fails after the crew has already launched from Earth, mission controllers face an impossible situation. The crew is in transit. They cannot turn around. They will arrive at Mars in months. And the propellant supply that was supposed to bring them home is incomplete or compromised. But if that rocket fails, the mission ends there. Consider the cryogenic storage problem, because it represents a slow-motion threat that could undermine even a perfectly functioning production system. Methane becomes liquid at approximately -161 degrees Celsius at standard pressure. Liquid oxygen boils at -183 degrees Celsius. These propellants must be kept at or below these temperatures for years on the Martian surface. Not days, not weeks, years, the entire duration of the pre-crew production phase plus the 500-day surface stay. Mars does get cold. Surface temperatures at equatorial landing sites regularly drop below -80 degrees Celsius at night and can plummet past -100 degrees during winter. But daytime temperatures at these same sites can climb above 0 degrees Celsius. The daily thermal cycle, cold enough to partially assist cryogenic storage at night, warm enough to challenge it during the day, creates expansion and contraction stresses on tank materials, insulation layers, and connecting plumbing. Over hundreds of Martian sols, this thermal cycling accumulates. Microfractures in weld seams, fatigue in metal bellows, degradation of multi-layer insulation. These are predictable long-term effects that terrestrial cryogenic engineers manage through inspection and maintenance. On Mars, there is no inspection. There is no maintenance, not until the crew arrives, and by then the damage may be done. A slow leak might be the cruelest failure mode of all. The ISRU system could function perfectly, producing propellant at the required rate. The storage tanks could appear nominal in every telemetry reading sent back to Earth. Tank pressure readings might remain within expected bounds, because the leak rate is small enough that ongoing production masks the loss. But if methane or oxygen is slowly venting into the Martian atmosphere, seeping through a degraded seal or a hairline crack at a rate too low to trigger alarms, the crew could arrive to find tanks that are partially full. Perhaps 80%, perhaps 70%. Enough propellant for a partial ascent that reaches the upper atmosphere before the engines starve, but not enough to achieve orbital velocity and reach the waiting return vehicle. Boil-off is the thermal cousin of leakage. Even with excellent insulation, and modern multi-layer insulation systems are remarkably effective, Some thermal energy will inevitably migrate through the tank walls and into the cryogenic propellant. This energy causes a small fraction of the liquid to vaporize into gas, increasing tank pressure. In terrestrial applications, this boil-off gas is either vented or reliquefied by active refrigeration systems called cryocoolers. On Mars, venting wastes propellant. Reliquefaction requires power that competes with the ISRU system for the limited energy budget. Every watt spent on cryocoolers is a watt not spent on producing new propellant. The engineering trade-off is real. Mission planners must choose between accepting some boil-off loss and overproducing propellant to compensate, or investing mass and power in active refrigeration that keeps the stored propellant intact but reduces overall production capacity. Current estimates suggest that without active thermal management, boil-off rates for methane and oxygen on the Martian surface could consume between 1 and 5% of stored propellant per month, depending on tank design and insulation quality. Over a 2.5-year pre-crew production phase, unmanaged boil-off could evaporate a significant fraction of the propellant produced. This makes active cryogenic management essentially mandatory, which means the mission depends not only on the ISRU chemical plant, but also on a separate refrigeration system that must operate continuously alongside it. Now, let me walk you through the failure scenario that mission planners consider most carefully, because it illustrates how the ISRU dependency creates risks that compound in ways traditional spaceflight has never faced. The ISRU system has been operating on Mars for 14 months. Telemetry indicates normal performance. The Sabatier reactor is converting carbon dioxide and hydrogen into methane at the expected rate. The electrolysis cells are splitting water into oxygen and recycled hydrogen. Propellant production is tracking to plan, slightly ahead of the minimum required timeline. On Earth, mission controllers are cautiously optimistic. The crew has already launched and is 6 months into the transit to Mars. They are committed. There is no turning back the trajectory, and fuel constraints of interplanetary travel do not permit reversals. The spacecraft does not carry enough propellant to abort and return to Earth. Once the trans-Mars injection burn is complete, Mars is the only destination. During month 15, a regional dust storm develops in the southern hemisphere and expands northward toward the ISRU site. The storm is not one of the rare global events that encircle the entire planet, but it is substantial. A regional system spanning several thousand kilometers that reduces solar energy at the surface by roughly 60% for 3 weeks. The ISRU plant, powered by a solar array sized with some margin, but not enough for a sustained 60% reduction, drops to minimal operation. The Sabatier reactor, which requires consistent thermal management to maintain its operating temperature, cycles down. When the storm clears and solar power recovers, the system resumes, but the repeated power cycling has caused a thermal shock to the reactor's catalyst bed. The nickel catalyst has partially sintered, its microscopic porous structure has fused together under the repeated heating and cooling cycles, reducing the effective surface area available for the chemical reaction. The reactor still works, it just works slower. Production rate drops to 70% of its nominal capacity. Mission controllers on Earth detect the reduced output in telemetry. They run projections. At the new production rate, the system will generate only 82% of the required propellant by the time the crew arrives. They begin evaluating options. Can the crew extend their surface stay to allow more production time? Possibly the habitat's consumables have some margin built in. But the margin is measured in weeks, perhaps 2 months at the outside, not the many additional months that would be needed to close an 18% deficit at 70% production rate. Can the Ascent Vehicle fly with less propellant? In theory, if the crew jettisons equipment, scientific samples, and non-essential gear to reduce the vehicle's mass at launch. But every kilogram in the Ascent Vehicle's mass budget was already optimized during the design phase. There is very little discretionary mass to shed. The crew cannot leave behind their pressure suits or their life support hardware. The crew lands. They inspect the propellant stores. 84% of targets, slightly better than the worst-case projection, but still critically short. The ISRU system continues operating at its reduced capacity throughout the surface stay. The crew has roughly 500 days on the surface. If the system maintains 70% output for the full duration, they will accumulate approximately 96% of the required propellant by the departure date. 96% might be enough if the ascent trajectory is optimized aggressively, burning less propellant during ascent at the cost of reaching a lower, less optimal orbit, which then requires the Earth return vehicle to descend from its planned parking orbit to meet them. This is feasible in principle, but introduces new risks to the rendezvous sequence. The return vehicle must carry sufficient fuel for an unplanned orbit-lowering maneuver. Its navigation system must accommodate a different rendezvous geometry. The margin that existed in the planned profile evaporates, or the catalyst could degrade further. If a second dust event occurs and regional storms on Mars are not rare, the additional thermal cycling could push the sintering past a tipping point. If production drops to 50% of nominal, the arithmetic stops working entirely. No trajectory optimization, no mass reduction, no extended surface stay will close the gap. The crew will be on Mars with a vehicle that has insufficient fuel to reach orbit. Everything depends on that launch off Mars. But the launch depends on the fuel, and the fuel depends on a chemical plant that must operate on an alien world, uncrewed for years, with no possibility of hands-on repair if a critical component fails before the crew arrives. This dependency chain is what separates Mars from every previous destination in human spaceflight. Apollo crews carried their return fuel with them. Space station crews have their Soyuz capsule always fueled, always ready, always attached to the station, as a lifeboat that can undock and deorbit within minutes. Even Antarctic research stations, the closest terrestrial analogy to Mars surface operations, can be resupplied by air during emergencies. Mars offers no such safety net. The return capability must be built in place, molecule by molecule, from the thin alien air. Some mission architectures attempt to mitigate ISRU risk by sending redundant systems to independent production plants instead of one, each capable of meeting the full propellant requirement on its own. If one plant fails, the other continues producing. This is sound engineering philosophy. Redundancy is how aerospace systems traditionally manage risk. Aircraft have multiple engines. Spacecraft have backup computers. The space shuttle had 3 hydraulic systems. You do not bet the crew's lives on a single point of failure if you can avoid it. But redundancy on Mars comes at enormous cost. 2 ISRU plants mean roughly double the mass that must be delivered to the Martian surface, which means a larger or additional cargo lander, which means more heavy lift launches from Earth, which means more orbital assembly or refueling operations, which means more cost and more schedule risk. The expense of a single Mars cargo delivery is measured in billions of dollars. Doubling the ISRU payload doubles a significant fraction of the total mission cost. And even redundancy has limits when the systems share an environment. Both plants sit on the same patch of Martian surface. Both breathe the same dusty atmosphere. Both depend on the same solar energy or the same nuclear reactor. A global dust storm reduces power to both simultaneously. Contamination of the atmospheric intake, perhaps from an unexpectedly corrosive dust chemistry, or an unanticipated electrostatic clogging of the intake filters, could disable both plants at once. A severe seismic event, Mars does experience Marsquakes, as the InSight lander's seismometer confirmed, could damage both installations simultaneously. Common mode failures, where a single external event defeats all redundant systems because they share a vulnerability, represent the nightmare scenario of reliability engineering. They are exactly the kind of failures that are hardest to predict and hardest to prevent, because they originate in the environment rather than in the hardware. The temperature extremes on Mars create particular challenges for the mechanical components of an ISRU plant that go beyond the cryogenic storage problem. The Sabatier reactor itself operates at 300 to 400 degrees Celsius internally, while the external environment cycles through its brutal daily temperature swing. This creates severe thermal gradients across the reactor, housing hundreds of degrees of difference between the hot interior and the frigid Martian night on the other side of the insulation. Seals at the interface between hot and cold zones experience differential expansion. Metal components on the hot side grow, while components on the cold side contract. Over hundreds of sols, this stress cycle accumulates, pushing materials toward fatigue limits that were characterized in Earth laboratories but have never been validated in the actual Martian environment. Valves deserve special attention because an ice-rue plant contains dozens of them, and each one is a potential failure point. Valves control the flow of gases and liquids throughout the system: atmospheric intake valves, reactor feed valves, product separation valves, propellant transfer valves, tank isolation valves. Each valve must open and close reliably after sitting in near vacuum conditions with temperature swings of 150 degrees, potentially contaminated by Martian dust that has infiltrated despite every protective measure. A valve that sticks open allows uncontrolled flow. A valve that sticks closed stops production. A valve that leaks wastes propellant or reactants. On Earth, a stuck valve is a maintenance item. A technician replaces it and production resumes. On Mars, before the crew arrives, a stuck valve could be a mission-ending event. On Earth, industrial chemical plants undergo regular maintenance. Technicians walk the lines daily, checking for leaks, listening for unusual sounds, inspecting gauges, and replacing worn components on a preventive schedule. The entire discipline of industrial maintenance exists because complex chemical systems inevitably degrade and require human intervention to remain operational. On Mars, before the crew arrives, the ISRU plant operates with no maintenance capability whatsoever. It must be designed to survive and function for over 2 years without a single human hand touching it. This requires a level of autonomous reliability that exceeds anything currently demonstrated in industrial practice or planetary surface operations. The MOXIE experiment demonstrated that the basic electrochemistry works on Mars. That accomplishment should not be diminished. It answered a genuine scientific question about whether Martian atmospheric conditions would introduce unexpected complications to the electrolysis process. They did not. The chemistry performed as predicted. But what MOXIE did not demonstrate is the scale, the duration, the autonomous operation, the cryogenic storage, the power management, the thermal cycling resilience, or the overall system reliability required for a life-critical propellant production system. The gap between MOXIE and a flight-ready ISRU plant is comparable to the gap between the Wright brothers' 12-second flight at Kitty Hawk and a modern airliner crossing the Atlantic carrying 300 passengers. Through a thunderstorm, the underlying principles connect them. The engineering maturity separating them spans a century of development. But none of this matters if the ascent vehicle does not start. The ISRU system is the supply chain. The ascent vehicle is the machine that uses what the supply chain built. And if that machine fails on the day it matters most, the one day in the entire mission when it must perform, the supply chain's success becomes irrelevant. The propellant sits in its tanks, fully produced, perfectly stored, chemically pristine. And the crew sits on the surface, with a full tank and a dead engine, watching the departure window close. Manufacturing your way home is the boldest bet in the history of human exploration. Not because the chemistry is uncertain, it is not. Not because the engineering is theoretically impossible, it is not. But because the chain of systems that must all work in sequence, over years, without human maintenance, in an environment that has been tested only by robots, creates a cumulative probability of failure that no previous human mission has ever accepted. It is a bet that chemistry obeys the same rules on Mars as it does on Earth, that autonomous systems can operate for years without critical failure, that cryogenic propellants can be stored in an alien thermal environment without unacceptable degradation, that the production timeline will not be fatally disrupted by dust storms, equipment aging, or conditions that no Earth-based test program anticipated, that every valve will open, every seal will hold, every reactor will maintain temperature, every compressor will turn, every electrolysis cell will split its molecules for years, without rest, without repair, without anyone watching. It is a bet that must be won, Because if it is lost, there is no second wager, there is no backup plan, there is no alternative supply of propellant waiting on another continent or in another warehouse. There is only Mars and the thin alien air, and the machine that must turn that air into a ride home, and the crew will not know whether the bet paid off until they are already there. Here is a detail that almost never appears in Mars mission graphics or public presentations. When astronauts board the Mars Ascent Vehicle for departure, they will be climbing into a spacecraft that has been sitting on the Martian surface for roughly 3 years. 3 years exposed to ultraviolet radiation unfiltered by any meaningful ozone layer. Mars lacks the thick atmospheric blanket and magnetosphere that protect Earth's surface from the sun's most damaging wavelengths. On Earth, the ozone layer absorbs virtually all ultraviolet C radiation and most ultraviolet B. On Mars, the full spectrum of solar ultraviolet light reaches the surface essentially unimpeded. This radiation degrades polymers, weakens adhesives, embrittles rubber seals, and damages electronic components over time. 3 years of continuous UV exposure is not a trivial environmental factor. It is a materials science problem with no terrestrial equivalent at this intensity and duration for flight-critical hardware. 3 years of thermal cycling between freezing nights and comparatively warm days. 3 years of fine, electrostatically charged dust settling into every crevice, every seal, every connector that is not hermetically sealed and potentially some that are, because Martian dust particles measure as small as 1 to 2 micrometers, fine enough to penetrate seals that would stop terrestrial contaminants. 3 years without a single inspection by a qualified technician, without a single component replacement, without a single system test at full operational power, and then they will ask it to do the hardest thing it was ever designed to do. On Earth, a rocket launch is the culmination of months of preparation by thousands of people. Consider what happens before a Falcon 9 lifts off from Cape Canaveral. The vehicle is assembled in a climate-controlled integration facility. Each stage is transported to the pad on a transporter erector, connected to ground support equipment through multiple umbilicals that supply power, data, propellant, and thermal conditioning. The launch pad itself is an industrial complex, flame trenches, water deluge systems, lightning protection towers, propellant storage farms, high-pressure gas supplies, and redundant communications links to the Mission Control Center. During the countdown, hundreds of sequential checks are performed by dozens of specialized engineers. Propellant loading is monitored by dedicated teams watching temperature, pressure, and flow rate data in real time. Any anomaly, no matter how minor, can trigger a hold or a scrub. The vehicle sits in a controlled environment, attended by ground systems, until the final seconds before ignition. On Mars, none of this infrastructure exists. Not one element of it. The Ascent Vehicle is its own launch pad, its own ground support equipment, its own mission control. The crew performs final checks using whatever diagnostic systems are built into the vehicle. Internal pressure readings, valve position indicators, battery voltage levels, guidance system alignment data. But they cannot physically inspect the engine's turbopumps, which spin at tens of thousands of revolutions per minute and must maintain microscopic clearances between rotating and stationary components. They cannot visually examine the combustion chamber's inner lining for cracks or erosion. They cannot verify the integrity of propellant feed lines buried inside the vehicle's thermal protection structure. They cannot pull a suspect component and replace it with a spare from a nearby warehouse, because there is no warehouse. They must trust that the hardware survived 3 years on Mars and will function now, at this moment, on this one attempt. There is no second attempt. There is no pad abort in any current Mars Ascent Vehicle design. There is no return to a vehicle assembly building for troubleshooting. If the engine does not ignite, or if it ignites and then shuts down during the ascent burn, or if a propellant valve sticks in the wrong position, or if a turbopump bearing seizes after thermal damage from years of temperature cycling, the crew is on Mars permanently. Let me describe what must happen in the minutes following a successful ignition, because the demands on this vehicle do not relax after the engine lights, they intensify. The Ascent Vehicle's engine fires. For the first several seconds, the vehicle climbs vertically, clearing the surface and any nearby terrain, the habitat modules, solar arrays, and ISRU equipment that may surround the launch site. The initial acceleration is modest compared to an Earth launch. Mars's gravity is 38% of Earth's, so less thrust is needed to overcome the gravitational pull at liftoff. A vehicle that weighs 15 tons on Mars would weigh roughly 40 tons on Earth, so the engine can be smaller and less powerful than an equivalent Earth launch system. This sounds like an advantage, and in terms of engine sizing it is, but lower gravity also means lower weight pressing the vehicle down onto its launch mount, which changes the separation dynamics. The vehicle lifts off at lower thrust, meaning any lateral force wind, asymmetric thrust, a frozen hold-down bolt releasing unevenly has a proportionally larger effect on the vehicle's initial trajectory. Within seconds of clearing the surface, the vehicle must begin a gravity turn. This is the controlled maneuver where the vehicle pitches gradually from its initial vertical orientation toward a more horizontal flight path, trading altitude for horizontal velocity. Orbital mechanics demands this. Orbit is not about getting high. It is about going fast enough that as you fall toward the planet's surface curves away beneath you at the same rate. Reaching orbital velocity requires the vehicle to accelerate primarily horizontally, not vertically. The gravity turn is how launch vehicles accomplish this transition, using gravity itself to gradually tilt the trajectory from vertical to near horizontal over the course of the ascent burn. On Earth, the gravity turn is assisted by aerodynamic forces. The atmosphere provides a restoring force that helps stabilize the vehicle's orientation during the pitch maneuver. If the vehicle drifts slightly off its intended attitude, aerodynamic pressure on the rocket body pushes it back toward the correct orientation, like a weather vane aligning with the wind. The thicker the atmosphere, the stronger this stabilizing effect. On Mars, the atmosphere provides roughly 1% of this aerodynamic stabilization. The vehicle must maintain its orientation almost entirely through thrust vectoring, physically swiveling the engine nozzle to redirect the thrust force and steer the vehicle. This demands precise continuous actuation of the engine gimbal system. The actuators that swivel the nozzle, typically hydraulic or electromechanical systems, must respond within milliseconds to commands from the guidance computer. These actuators have been sitting on Mars for 3 years, their seals exposed to dust, their lubricants subjected to temperature extremes, their electrical connections potentially degraded by the same UV radiation and thermal cycling that affects every other system on the vehicle. Any error in the guidance software, any sluggishness in the thrust vector actuators, any unexpected wind shear during the critical first 60 seconds of flight, and the vehicle's trajectory begins to diverge from the planned path. The guidance system will attempt to correct, commanding larger gimbal deflections to bring the vehicle back on course. But larger deflections mean more fuel spent on steering rather than acceleration, and the fuel budget has no room for significant unplanned expenditures. On Earth, if an ascent trajectory goes badly wrong, there are options. The crew can activate a launch escape system, a separate solid rocket motor that pulls the crew capsule away from the failing launch vehicle. This system was used on a Soyuz mission in 2018 when the rocket suffered a booster separation failure. The crew survived. Even without a launch escape system, crews in low Earth orbit can potentially reach emergency landing zones. The abort modes are well defined and rehearsed. On Mars, there is no launch escape system in any current MAV design concept. The mass penalty of adding one, a separate escape motor, a separable crew capsule, a parachute system for Mars landing, a heat shield would be prohibitive. The ascent vehicle is already mass-constrained to an extreme degree. Every kilogram devoted to an abort system is a kilogram taken from propellant, structure, or life support. And even if an escape system existed, where would the crew go? They cannot parachute to a safe landing on Mars without a dedicated landing system. They cannot splash down in a Martian ocean. There is no downrange recovery zone. The ascent is committed from the moment of ignition. Every second that follows must go right. The target orbit depends on the mission architecture, but a representative figure is a low Mars orbit at roughly 200 to 400 kilometers altitude. To reach this orbit, the vehicle must achieve a velocity of approximately 3.5 to 3.8 kilometers per second. For context, low Earth orbit requires roughly 7.8 kilometers per second, so the Mars orbital velocity requirement is less than half of Earth's. This reflects Mars's lower mass and correspondingly weaker gravitational field, but 3.5 kilometers per second is still nearly 13,000 kilometers per hour. Achieving this velocity requires sustained, precise engine performance over several minutes of powered flight. The engine must deliver its rated thrust consistently from ignition through main engine cutoff. It must maintain the correct mixture ratio of fuel to oxidizer throughout the burn to ensure efficient combustion. It must not experience any of the instabilities, combustion oscillations, injector erosion, turbopump cavitation that rocket engineers spend years testing and tuning out of engines on Earth. If thrust is lower than expected, perhaps because partially clogged fuel injectors are reducing the propellant flow rate, or because the methane's thermodynamic properties are slightly different from the design specification due to trace impurities introduced during the ISRU production process, or because a turbopump is underperforming after bearing degradation, the vehicle will not reach orbital velocity. It will follow a suborbital ballistic trajectory. It will rise, reach an apex, and then fall back toward the Martian surface. There is no recovery from this scenario. The vehicle has no landing system. A suborbital ascent that falls short of orbital velocity is not survivable. If that rocket fails, the mission ends there. Now consider what must happen after the vehicle reaches orbit, because achieving orbital velocity is necessary but not sufficient. The ascent vehicle must reach the correct orbit, the specific orbit where the Earth return vehicle is waiting. This is not a general-purpose orbit. It is a precisely defined trajectory characterized by its altitude, its inclination relative to Mars's equator, and its phase, the vehicle's position along the orbital path at any given time. Apollo faced a similar rendezvous requirement, but Part 1 described how much simpler the lunar version was. No atmosphere, a 60-mile orbit, and a rendezvous completed in hours. What matters here is a difference we have not yet examined. During Apollo rendezvous, the communication delay between the Moon and Earth was roughly 1.3 seconds each way. Ground-based tracking stations could determine both vehicles' positions to high accuracy and relay updated navigation data in near real time. If something went wrong, controllers could intervene within seconds. And if the rendezvous failed entirely, the command module pilot could potentially have flown down to retrieve the crew, a contingency that was studied though never needed. On Mars, every one of these advantages evaporates. The communication delay we discussed in Part 1, 4 to 24 minutes each way, 8 to 48 minutes for a round trip, becomes most dangerous during rendezvous. When two vehicles are closing at meters per second, and the crew needs real-time position updates to execute docking, a 48-minute communication loop is not merely unhelpful, it is irrelevant. By the time Earth-based controllers see what is happening, it has already happened. The rendezvous must be executed autonomously by the onboard computers or manually by the crew using instruments aboard the vehicle. Mission Control can offer strategic advice and long-term trajectory planning. It cannot fly the approach. The ascent vehicle must carry its own navigation system capable of determining its position and velocity in Mars orbit and then guiding itself to a successful rendezvous. This system would likely combine inertial measurement units, gyroscopes, and accelerometers that track the vehicle's motion with star trackers that determine absolute orientation by photographing known star fields, and a proximity sensor system such as radar or LiDAR for the terminal approach phase, when the two vehicles are within a few kilometers of each other. Each of these systems faces specific challenges after 3 years on Mars. Inertial measurement units drift over time. Their gyroscopes accumulate small angular errors that, if uncorrected, compound into significant navigation inaccuracies. On Earth, IMUs are regularly calibrated against external references. On Mars, the vehicle's IMU would need to be calibrated using star tracker data before launch, which requires the star tracker to function properly. and star trackers need clean optical surfaces to image star fields accurately. 3 years of Martian dust settling on the star tracker's lens or window, even in a protected enclosure, could degrade its performance. If the star tracker cannot achieve a precise fix, the IMU calibration is compromised, and the initial navigation state at launch contains errors that propagate through the entire ascent and rendezvous sequence. The rendezvous follows a sequence that has been refined through decades of orbital mechanics experience. The ascent vehicle reaches an initial orbit that is lower than the Earth return vehicle's parking orbit. In a lower orbit, the ascent vehicle moves faster, a counterintuitive consequence of orbital mechanics, where objects closer to a gravitational body orbit at higher velocities. This means the ascent vehicle gradually overtakes the Earth return vehicle. When the geometry is right, the ascent vehicle performs a series of phasing burns, small engine firings that raise its orbit incrementally, matching first the altitude and then the phase of the target vehicle. The approach proceeds through a series of waypoints at decreasing distances, with the closing rate carefully managed down from kilometers per second to meters per second to centimeters per second for the final docking approach. This sequence has been performed successfully thousands of times in Earth orbit. Progress cargo vehicles dock with the International Space Station routinely. SpaceX Dragon capsules approach and berth with the station using a combination of GPS navigation and proximity sensors. The Gemini program demonstrated orbital rendezvous in 1965. The procedure is mature, well understood, and reliable in Earth orbit, with ground-based tracking support, ample fuel reserves, and multiple retry opportunities. In Mars orbit, the margins narrow dramatically. The ascent vehicle carries limited fuel for orbital maneuvers. Its propellant was budgeted for the ascent burn and the rendezvous sequence, with reserves measured in single-digit percentages above the nominal requirement. Every phasing burn, every correction maneuver, every unplanned adjustment consumes propellant from a finite supply that cannot be replenished. In Earth orbit, a spacecraft with a failed docking attempt simply backs away, waits 90 minutes for the next orbital pass, and tries again. The fuel cost of multiple attempts is budgeted into the mission. In Mars orbit, 2 or 3 failed approaches might exhaust the remaining propellant margin. The ascent vehicle would then be in orbit, unable to maneuver, unable to reach the Earth return vehicle, and unable to return to the surface. This scenario, crew alive in Mars orbit but unable to dock, is in some respects worse than being stranded on the surface. On the surface, the crew has a habitat with life support, stored food and water, the ISRU system potentially still producing oxygen for breathing, and the psychological comfort of solid ground beneath their feet. In Mars orbit, they have a small ascent vehicle with life support capacity measured in days, not months. No additional food beyond emergency rations. No long-term atmospheric recycling. No ability to land. And a return vehicle hanging in the same sky, visible through the window, transmitting telemetry that they can read, close enough that they could describe its docking port markings over the radio to mission control but unreachable. Everything depends on that launch off Mars and on the rendezvous that follows it. Each step in the chain depends on the step before, and failure at any point produces the same outcome. The timing window for rendezvous is constrained by a factor that exists entirely outside the crew's control, the trans-Earth injection window. The Earth return vehicle must fire its engines at a specific time to leave Mars orbit on a trajectory that intersects Earth's orbital path months later. This departure timing is dictated by the positions and velocities of 2 planets orbiting the Sun at different rates and different distances. The geometry opens a window that lasts a few weeks, with the optimal departure date offering the most fuel-efficient trajectory and the off-optimal dates requiring progressively more propellant for less efficient paths. If the rendezvous sequence runs long, if the ascent launch is delayed by even a few days for weather or systems checks, if the phasing burns require more time than planned because of orbital insertion errors, if docking requires multiple attempts over several days, the departure window begins to close. Each day of delay pushes the departure further from the optimal date, requiring more propellant for the trans-Earth injection burn. The Earth return vehicle carries a finite propellant supply, that was sized for the planned departure profile plus modest reserves. Enough delay erodes that reserve entirely, making the departure impossible until the next window opens 26 months later. 26 months in Mars orbit. In a vehicle provisioned for a 6 to 9 month transit, the arithmetic of survival does not close. Let me walk through the engine ignition failure scenario in detail, because it illustrates the absolute finality that distinguishes this mission from everything that has come before in human spaceflight. The crew has been on Mars for 480 days. The ISRU system has produced sufficient propellant, the tanks verified full, the propellant quality tested and confirmed within specification. All pre-flight system checks show nominal readings. The crew has spent the preceding days configuring the ascent vehicle for flight, powering up avionics, calibrating the inertial measurement unit using star tracker data, pressurizing the propellant tanks to flight pressure, and running automated diagnostic sequences on every accessible system. Everything reads green. The crew seals themselves inside the Mars Ascent Vehicle. The hatch closes, the cabin pressurizes, they strap into their seats. The final countdown sequence begins, managed by the onboard flight computer. At T-10 seconds, the flight computer verifies all systems one final time. At T-3 seconds, the ignition command is sent to the engine controller. Nothing happens. The engine controller receives the ignition signal. It commands the main propellant valves to open. The valves actuate telemetry, confirms propellant flow to the combustion chamber. The controller simultaneously commands the ignition system to fire. In many engine designs, initial ignition is accomplished using either a pyrotechnic charge, a chemical device similar to a very large match head, or a spark igniter system that produces an electrical arc in the combustion chamber. The pyrotechnic charge fires, or the spark igniter arcs. But combustion does not initiate. The engine controller's combustion chamber pressure sensor reads ambient, no rise in pressure, no evidence that the propellant has ignited. The flight computer, detecting no chamber pressure rise within the expected time frame, executes an automatic abort. Propellant valves slam shut. The ignition system safes. The crew sits in silence as the vehicle's status displays update to show an aborted launch attempt. What went wrong? The crew begins troubleshooting from inside the vehicle, reviewing telemetry logs and diagnostic data. The propellant valves opened correctly. Flow sensors confirmed propellant reached the combustion chamber. The ignition system fired, but the propellant did not ignite. Several possibilities exist, and this is where the 3-year exposure problem becomes concrete. Perhaps the pyrotechnic igniter, despite being sealed in a protective canister, has degraded. Pyrotechnic compounds are sensitive to moisture, and while the Martian atmosphere contains very little water vapor, typically less than 1% relative humidity by Earth standards, it is not zero. Over 3 years, trace moisture migrating through imperfect seals could have partially decomposed the igniter's chemical charge. It produced a flash, but not enough energy to initiate sustained combustion. Perhaps the igniter functioned correctly, but the propellant reaching the combustion chamber was not in the expected state. If the methane contained dissolved carbon dioxide absorbed during the ISRU production process, an impurity that ground-based purification was supposed to remove but did not fully eliminate its combustion characteristics, could differ from the design specification. The flame front initiates but quenches before reaching steady-state combustion. The crew exits the vehicle to attempt repairs. Some mission architectures include a limited set of spare components for the ascent vehicle's most critical systems: replacement igniters, spare valve actuators, backup sensor packages. The crew replaces the igniter assembly, following procedures they trained on during Earth-based simulations. They purge the propellant lines to clear any residual gas. They run a ground-level diagnostic on the engine's injector system, checking for blockages using pressure decay tests. Everything appears nominal. They re-enter the vehicle. They run the countdown again. The same result. Ignition signal sent. Propellant flow confirmed. No combustion detected. The new igniter is not the problem. Something else is preventing sustained ignition. The crew now faces a diagnostic challenge that would tax a team of engine specialists in a well-equipped test facility on Earth. The potential causes include injector blockage from crystallized propellant residue or dust contamination, a hairline crack in the combustion chamber allowing pressure to leak before reaching the ignition threshold, turbopump seal degradation preventing adequate propellant delivery pressure, a thermal control system failure that allowed propellant to partially vaporize in the feed lines, creating gas pockets that disrupt the combustion initiation sequence, or a subtle electronic fault in the engine controller's timing logic, causing the ignition pulse to arrive a fraction of a second too early or too late relative to propellant flow. Each of these requires different diagnostic tools, different repair procedures, and different spare parts. The crew has some tools, some spares, and extensive training, but they are not rocket engine mechanics. They are scientists, pilots, and mission specialists who received abbreviated engine maintenance training as one component of a multi-year preparation program that also covered geology, medicine, habitat repair, EVA procedures, and dozens of other disciplines. They are brilliant, capable, resourceful people working with limited equipment in an environment where a dropped wrench falls at Martian gravity and where every outdoor task requires a pressure suit that limits dexterity and visibility. On Earth, when a rocket engine fails to ignite during a test, the response involves a team of dozens of specialists, complete disassembly of the engine in a clean facility, forensic analysis of every component, and months of investigation before the next test. On Mars, the response involves 4 to 6 people, a limited toolkit, no clean room, no replacement engine, and a departure window that is closing. Everything depends on that launch off Mars, and the launch depends on a machine that must work perfectly after years of alien exposure, diagnosed and operated by people who are brave and brilliant, but who are working at the extreme edge of human capability in every dimension simultaneously. The navigation miscalculation scenario presents a different flavor of catastrophe, one where the engine performs flawlessly but the vehicle still fails to reach its crew home. Suppose the engine lights on the first attempt. Thrust is nominal. The gravity turn proceeds as planned. The guidance system commands the correct pitch and yaw maneuvers throughout the ascent burn. Main engine cutoff occurs on schedule, and the vehicle enters Mars orbit. By every immediate measure, the ascent was a success. But the initial state vector, the vehicle's precise position, velocity, and orientation at the moment of launch contained an error, not a large error. Not the kind of error that would be caught by gross diagnostics. A subtle error, perhaps a fraction of a degree in the launch platform's alignment relative to the Martian coordinate frame. Over 3 years, the landing platform shifted slightly. Thermal cycling of the ground beneath the vehicle expansion and contraction of Martian regolith over thousands of sol night temperature swings caused the platform to tilt by 1/10 of a degree. The vehicle's inertial navigation system, calibrated to the platform, accepted this tilt as level. The star tracker, which should have caught the discrepancy, had a dust-contaminated lens that reduced its angular accuracy just enough that the error fell within its noise floor. That 1/10 of a degree seems negligible. Over a multi-minute ascent burn, accelerating to 3.5 kilometers per second, it translates to an orbital insertion error. The vehicle reaches orbit, but the orbit is not quite right. The inclination is off by a fraction of a degree. The altitude is 12 kilometers lower than planned. The orbital phase, the vehicle's position along its orbit relative to the Earth return vehicle, is wrong by several minutes of arc, meaning the two vehicles are in slightly different orbits at slightly different positions. The guidance system recognizes the error and begins computing correction burns. This is expected. No real ascent achieves the exact planned orbit, and the rendezvous sequence always includes correction maneuvers. But the magnitude of the correction is larger than the nominal allocation. The inclination change alone, rotating the orbital plane by a fraction of a degree, is one of the most fuel-expensive maneuvers in orbital mechanics. Combined with the altitude correction and the phasing adjustment, the total correction burns consume most of the vehicle's remaining propellant reserve. The vehicle arrives in the vicinity of the Earth return vehicle within radar range, within communication range, close enough to track visually through the window, but it arrives with insufficient propellant for the final approach sequence. The closing maneuvers that reduce relative velocity from meters per second to centimeters per second require precise, controlled engine firings. Without adequate fuel, the vehicle cannot match velocity with the return vehicle. It drifts past, or it approaches too fast and the guidance system aborts the docking to prevent collision. 2 spacecraft in Mars orbit, one carrying the crew, one carrying the propulsion system, the supplies, and the trajectory home, separated by kilometers that might as well be light years, because the ascent vehicle has exhausted its ability to close the gap. Could the Earth return vehicle maneuver to rescue the situation? Possibly, if it carries sufficient fuel reserves and if its propulsion system can execute unplanned maneuvers. Some mission architectures design the return vehicle with enough capability to adjust its orbit for off-nominal rendezvous scenarios, but every kilogram of fuel allocated to rescue contingencies is a kilogram not available for the trans-Earth injection burn. The margin comes from somewhere, and the somewhere is usually the already thin reserve that protects against other contingencies during the months-long journey home. There is no good answer to this scenario. There are only less bad answers, each carrying its own risks, each consuming margins that were allocated to protect against other failures further down the chain. This is the architecture of the Mars return problem. Not a single dramatic failure, but a cascade of dependent systems where each link must hold, and where the failure of any one link engine ignition, guidance accuracy, fuel reserves, rendezvous navigation, docking execution produces an outcome that cannot be recovered from with the resources available. Every failure mode ends in the same place. Crew on Mars or crew in Mars orbit, alive but unable to return to Earth, beyond the reach of any rescue that could arrive in time to matter. The specifics differ. The result is identical, and every one of these failure modes involves technologies and operations that have never been tested at Mars, not once. The engine has never been ignited after 3 years on the Martian surface. The guidance system has never navigated a Mars ascent. The rendezvous has never been attempted in Mars orbit. The docking has never been performed at Mars distance from Earth, with its corresponding communication delay. Every element of the return chain will be attempted for the first time with human lives at stake. This is not how aerospace engineering normally operates. Normally, systems are tested exhaustively before crews fly them. Mercury, Gemini, and Apollo each flew multiple uncrewed test missions before carrying astronauts. The Space Shuttle conducted a 4-flight test program. SpaceX flew Crew Dragon to the space station uncrewed before putting astronauts aboard. The principle is simple. Demonstrate the system works before betting lives on it. For the Mars return, that principle demands uncrewed demonstration missions at Mars robotic ascent tests, autonomous rendezvous trials, ISRU validation over multi-year timescales. These demonstrations would cost billions of dollars and add years to the timeline. They would not generate the inspirational imagery that drives public support, but they would answer the questions that no simulation, no ground test, and no Earth orbit demonstration can answer. Does the engine ignite after 3 years on Mars? Does the guidance system navigate accurately using Mars-based references? Can 2 vehicles rendezvous and dock autonomously in Mars orbit with a 20-minute communication delay? Can the full-chain production, storage, ascent, rendezvous, docking, execute successfully from start to finish without human intervention? Until those questions are answered with hardware on Mars, the ascent vehicle remains the most dangerous assumption in human spaceflight. A machine that must work perfectly, on its first real attempt, after years of neglect, in an environment where failure is final. Even if everything works, the fuel is produced, the engine ignites, the ascent reaches orbit, the rendezvous succeeds, the docking is clean, the crew is still not safe. They are in Mars orbit, sealed inside the Earth return vehicle, and they face one more irreversible maneuver before they can even begin the journey home. The trans-Earth injection burn. This is the engine firing that accelerates the spacecraft out of Mars orbit and onto a transfer trajectory toward Earth. It is not a gentle nudge. It requires a velocity change of roughly 1.5 to 2.5 kilometers per second, depending on the specific trajectory chosen and the departure window available. To put that in context, 1.5 kilometers per second is approximately 5,400 kilometers per hour, a velocity change that requires sustained, precise engine performance over several minutes. The burn must happen at a precise point in the orbit, at a precise time, aimed at a precise heading. The geometry of the two planets, their relative positions, their relative velocities, their orbital inclinations, their distances from the Sun defines a narrow corridor through which the spacecraft must pass to reach Earth. That corridor is not a physical tunnel. It is a mathematical one, defined by the laws of celestial mechanics that have governed planetary motion since the solar system formed 4.5 billion years ago. Those laws are absolute. They do not accommodate human scheduling preferences. The departure window from Mars orbit is not a single moment. It spans a period of roughly 2 to 4 weeks, during which departure is possible, with the optimal date offering the most fuel-efficient trajectory. Departing on the optimal date means the trans-Earth injection burn requires the least propellant, leaving the most reserves for mid-course corrections during the transit home. Departing a few days before or after the optimum still works, but requires more propellant for a less efficient trajectory. Departing at the very edge of the window demands significantly more fuel, potentially consuming reserves that were allocated for mid-course navigation corrections. Departing after the window closes is not departing at all. Miss the window entirely, and the next opportunity does not arrive for roughly 26 months. 26 months in Mars orbit. Let that settle for a moment, because the implications are severe in ways that go beyond simple inconvenience. The Earth return vehicle is provisioned for a transit of 6 to 9 months, depending on the trajectory. Its life support system, the carbon dioxide scrubbers, the water recycling equipment, the oxygen generation system is sized for that duration with appropriate margins. Its food supplies are calculated for that crew size over that time. The thermal control system is designed to manage heat loads for a transit duration mission. The radiation shielding is adequate for a transit duration exposure. Every consumable aboard that vehicle has a finite lifespan calibrated to the planned mission profile. Extending a 6-month supply to cover 26 months is not achievable through rationing alone. The mathematics of human metabolism are unforgiving. A human body requires a minimum of approximately 1,200 to 1,500 calories per day to sustain basic biological functions: heart, lungs, brain, kidneys. Below that threshold, the body begins consuming its own muscle tissue for energy. Over weeks and months, malnutrition produces cognitive decline, immune system failure, and eventually organ damage. A crew of 4 consuming even minimal rations would exhaust a 6-month food supply in roughly 8 to 10 months of strict rationing, leaving 16 months with no food at all. Water cannot be recycled with perfect efficiency. The International Space Station's water recovery system achieves approximately 98% efficiency, a remarkable engineering achievement made possible by a brine processor added in 2023. But even a 2% loss per cycle compounds over time. Without resupply, water stores gradually diminish. Carbon dioxide scrubbers have finite chemical capacity. Lithium hydroxide canisters, the traditional backup scrubbing technology, are consumed as they absorb carbon dioxide and cannot be regenerated. Regenerable systems like the zeolite-based units on the ISS require power and periodic maintenance. If power systems degrade or maintenance capability is limited in a vehicle not designed for extended occupancy, carbon dioxide levels in the cabin will rise, producing headaches, impaired judgment, and eventually incapacitation. A crew stranded in Mars orbit for 26 months waiting for the next departure window would face a slow-motion survival crisis with no possibility of resupply. No cargo vehicle can reach Mars orbit on short notice. Even if a resupply mission were launched from Earth the moment the emergency was declared, it would arrive at Mars 9 months later at the absolute earliest, and only if a suitable launch vehicle and payload were available immediately, which they would not be. No space agency maintains a standing Mars emergency resupply capability. The cost of keeping such a capability ready would exceed the budget of most national space programs, and no such emergency mission has ever been planned, because the entire architecture assumes the departure window will be met. The trans-Earth injection burn itself demands that the Earth return vehicle's propulsion system function correctly after spending an extended period in Mars orbit. Consider the timeline. In most mission architectures, the Earth return vehicle arrives at Mars before the crew. It enters Mars orbit and waits perhaps for several months if it arrives in the same transfer window as the cargo, or for over 2 years if it is sent in an earlier window to provide additional safety margin. The crew then descends to the surface, spends roughly 500 days conducting their mission, ascends and docks with the return vehicle. By the time the crew boards the Earth return vehicle and prepares for the trans-Earth injection burn, the vehicle may have been orbiting Mars for 2 to 3 years. During those years, the vehicle's propulsion system sits dormant. Propellant in the tanks is subject to slow thermal effects from solar heating and radiative cooling. Seals in the engine's propellant valves may degrade. Lubricants in the engine gimbal actuators may migrate or evaporate in the vacuum of space. The vehicle's attitude control thrusters, small engines used to maintain orientation during the long wait, consume propellant from a finite supply, reducing the margin available for the main departure burn. The vehicle's batteries discharge and recharge through thousands of orbital day-night cycles. Its star trackers accumulate radiation damage from solar and cosmic particles. Its computer systems run continuously, and any software fault that emerges during the dormant period must be identified and patched from Earth across a multi-minute communication delay. The Earth return vehicle must wake up and perform. After years of orbital dormancy, it must execute a burn that is the crew's only path home. Orbital mechanics impose another constraint on the return trajectory that is not immediately obvious to anyone outside the field. The path home is not a straight line from Mars to Earth. It is an elliptical arc, a transfer orbit that takes advantage of the Sun's gravitational field to curve the spacecraft's trajectory from one planetary orbit to another. The most common version is a Hohmann transfer, or a variant called a Type 1 or Type 2 trajectory, depending on the angular distance the spacecraft traverses around the Sun during the journey. The spacecraft does not fly to where Earth is at the moment of departure. It flies to where Earth will be 6 to 9 months later, when the spacecraft arrives at Earth's orbital distance from the Sun. This means the trans-Earth injection burn must aim the spacecraft at a point in empty space where Earth does not yet exist, a point defined entirely by mathematical prediction of where Earth's orbit will carry it months into the future. The prediction itself is straightforward. Planetary orbits have been calculated with extraordinary precision for centuries. NASA's Jet Propulsion Laboratory maintains ephemeris tables that specify the positions of all major solar system bodies to accuracies measured in meters over timescales of decades. Predicting where Earth will be in 7 months is a solved problem in celestial mechanics. What is difficult is executing the burn with sufficient precision to hit that predicted point. The target Earth's gravitational sphere of influence is approximately 1.5 million kilometers in diameter, which sounds large. But the spacecraft must approach from a distance of tens of millions to hundreds of millions of kilometers, depending on the specific trajectory. A pointing error of 1/10 of a degree at the moment of the trans-Earth injection burn translates to a missed distance of hundreds of thousands of kilometers at Earth arrival. 1 degree of error could mean missing Earth entirely and sailing past into interplanetary space on a trajectory that does not return. Course correction burns during the transit can compensate for initial errors. These mid-course corrections are standard practice for every interplanetary mission. Robotic spacecraft routinely execute them using onboard navigation data refined by ground-based tracking through NASA's Deep Space Network, a collection of large radio antennas in California, Spain, and Australia that can track spacecraft across the solar system with extraordinary precision. The same tracking infrastructure would support a crewed Mars return, but each mid-course correction requires propellant, and the return vehicle carries limited reserves for these maneuvers. The propellant budget allocates a specific mass for mid-course corrections based on expected initial errors and navigation accuracy. If the trans-Earth injection burn is less accurate than planned, perhaps because the engine's thrust was slightly off nominal, or because the vehicle's attitude was not perfectly aligned, at ignition the required corrections may exceed the allocated propellant budget. The crew's onboard navigation system must track the spacecraft's position throughout the 6 to 9 month transit using a combination of star sightings for attitude determination, sun sensors for rough position estimation, and radio tracking from the Deep Space Network for precise trajectory determination. This tracking and navigation capability exists and has been refined over decades of interplanetary missions. But for a crewed mission, the consequences of navigation failure are categorically different from robotic missions. A robotic probe that misses Earth flies past into deep space and is lost. The mission team is disappointed. Papers are written about what went wrong. Careers are affected, but nobody dies. A crewed vehicle that misses Earth carries human beings past their home planet and into a solar orbit from which there is no return. A fate so specific in its horror that it has been studied by psychologists as one of the most extreme scenarios in the literature of isolation and confinement research. The transit home takes 6 to 9 months, during which the crew lives in a habitable volume comparable to a large recreational vehicle. The psychological demands of this phase are genuine months of confinement, separation from family, awareness that the nearest hospital is on a planet receding behind them, and the cumulative stress of a mission that has already demanded more of them than any human beings have ever endured. But these are challenges of human endurance rather than engineering, and the focus of this story remains on the engineering chain that must hold. But none of this matters if the ascent vehicle does not start. That sentence has followed us through this entire story like a gravitational pull, bending every other consideration back toward the same central point. It is time to face its full implications and ask the question this story has been building toward. Is the problem solvable? Let me first describe the current state of engineering readiness, because the answer depends on understanding how far we have come and how far we have yet to go. NASA's Artemis program, which is currently working to return humans to the lunar surface, includes technology development objectives that feed directly into eventual Mars missions. The Space Launch System and Orion capsule provide the heavy lift Earth departure capability that would be needed for Mars transit. The Gateway Station planned for lunar orbit will test long-duration deep space habitation systems, life support, radiation monitoring, crew health management in an environment beyond low Earth orbit for the first time since Apollo. Lunar surface operations under Artemis will test surface power systems, crew mobility, and most relevant to the Mars return problem, ISRU. NASA plans to demonstrate lunar ISRU by extracting water from polar ice deposits in permanently shadowed craters and using electrolysis to produce oxygen and hydrogen. If successful, this will validate the foundational concept of manufacturing return propellant at the destination rather than carrying it from Earth. But the Moon is not Mars. The differences matter enormously for ISRU applicability. Lunar ISRU involves mining water ice from regolith and electrolyzing it, a process that uses solid-state raw material and well-understood electrochemistry. Martian ISRU involves compressing atmospheric gas, running high-temperature catalytic reactions, managing cryogenic liquefaction, and storing volatile propellants for years. The chemistry is different. The raw materials are different, the processing temperatures are different, the storage challenges are different, the power requirements scale differently. The timescales of different lunar ISRU demonstration missions will operate for weeks or months, while Martian ISRU must operate autonomously for years. Lunar ISRU experiments will provide valuable confidence in the general principle that propellant can be manufactured off Earth. They cannot validate the specific systems, processes, and reliability requirements of the Martian implementation. SpaceX's Starship architecture takes a fundamentally different approach to the return problem. Rather than a small, purpose-built ascent vehicle that must rendezvous with a separate return ship in orbit, SpaceX proposes landing the entire Starship vehicle on Mars, a massive stainless steel rocket standing approximately 50 meters tall with a dry mass of roughly 100 to 120 tons, and then refueling it on the surface for a direct return to Earth. This approach eliminates the separate ascent vehicle entirely. It eliminates the orbital rendezvous. It eliminates the need for a pre-positioned Earth return vehicle. The same vehicle that lands is the vehicle that leaves. In architectural terms, it is elegant. Fewer vehicles, fewer interfaces, fewer handoffs between systems, but it demands propellant production on a scale that dwarfs anything NASA has contemplated. A Starship returning from Mars to Earth would require approximately 1,200 tons of methane and liquid oxygen propellant. Producing 1,200 tons of cryogenic propellant on Mars requires not a chemistry experiment, but an industrial facility, a chemical plant operating at production rates that would be impressive on Earth, running for years on the surface of another planet. The power requirements for such production, estimated at several hundred kilowatts to multiple megawatts of continuous electrical power, would demand a nuclear power plant or a solar array field spanning hectares of Martian surface. Neither has been demonstrated at Mars. Neither has been demonstrated at the required scale anywhere outside of Earth. SpaceX has not publicly demonstrated Martian ISRU at any scale. The Raptor engine, which would power the return from Mars, has been tested extensively at the company's facilities in McGregor, Texas, and has flown on multiple Starship test flights from Boca Chica, Texas. It is a high-performance, full-flow staged combustion engine, burning methane and liquid oxygen, the same propellant combination that Martian ISRU would produce. The engine works. It has demonstrated remarkable thrust levels and restart capability in flight tests, but it has never been tested after sitting dormant for 3 years on the surface of another planet, exposed to dust, radiation, and thermal cycling. No engine of any type has ever been tested under those conditions. The gap between a Raptor firing in Texas after rolling out of a maintenance facility and a Raptor firing on Mars after 3 years of unattended exposure is a gap that cannot be closed by extrapolation. It must be closed by testing. NASA's Mars Sample Return program provides perhaps the most sobering perspective on the Mars Ascent Challenge. This mission, which aimed to bring a small canister of Martian rock and soil samples collected by the Perseverance rover back to Earth, was intended to include the first ever launch from the surface of another planet. The Mars Ascent Vehicle for this mission was a small, solid-fueled rocket designed to launch a canister roughly the size of a basketball into Mars orbit, where a separate orbiting spacecraft would capture it and carry it home. No crew, no life support, no rendezvous docking, just a capture using a containment mechanism, a relatively simple mission compared to crewed return. As of the most recent independent program reviews, Mars Sample Return has faced staggering budget growth and schedule delays. Original cost estimates of roughly $4 to $5 billion expanded to between $8 and $11 billion. The projected return date slipped from the early 2030s to potentially the late 2030s or beyond. NASA convened an independent review board that recommended fundamental restructuring of the program. The technical challenges designing a rocket that can operate after years on Mars, building an orbital capture system that can function autonomously around Mars, integrating the entire chain of events from surface launch to Earth delivery proved far more difficult than initial assessments suggested. If launching a basketball-sized sample container from Mars on an uncrewed solid rocket is an $11 billion engineering challenge that takes decades to execute, launching a crewed vehicle carrying 4 to 6 human beings with their life support systems on a liquid-fueled engine that must restart after years of dormancy into a precise orbit for rendezvous with a return ship that is a problem of a categorically different magnitude. The Mars return problem is not a single engineering challenge. It is a chain of dependent challenges, each of which must be individually solved, rigorously tested, independently validated, and then executed flawlessly in sequence on another planet with no possibility of real-time intervention from Earth. ISRU must work at industrial scale for years. Cryogenic storage must hold propellant within specification across thousands of thermal cycles. The ascent vehicle must survive the Martian environment and remain flight-worthy for the duration. The engine must ignite on demand after prolonged dormancy. The guidance system must navigate to a precise orbit using instruments that have been exposed to the same environment. The rendezvous must succeed with limited fuel and no ground-based tracking support. The docking must be clean on the first or second attempt. The trans-Earth injection must be timed precisely within the departure window. The return trajectory must be accurate enough that mid-course corrections do not exhaust the propellant budget. Any single failure in this chain ends the mission and ends the crew. In the entire history of human spaceflight, we have never attempted anything with this many sequential single points of failure, where the consequence of any single failure is total loss of crew, with no possibility of rescue within any survivable time frame. Apollo came closest, and Apollo is the appropriate benchmark, but Apollo carried all its fuel from Earth, eliminating the ISRU dependency. Apollo operated in vacuum, eliminating atmospheric interference during ascent. Apollo completed its rendezvous within hours, not days. Apollo maintained near real-time communication with ground control throughout the critical phases. Apollo was 3 days from Earth in an emergency. Mars is months from Earth in the best case. So is the problem solvable? The honest answer is yes, probably, but not quickly and not cheaply. And honesty requires acknowledging what that probably rests upon. Every individual technology in the return chain has been demonstrated in some form, at some scale, in some environment. The Sabatier reaction has been run in laboratories and on the Martian surface in miniature. Cryogenic propellant storage is well understood in terrestrial and orbital applications. Rocket engines are among the most thoroughly characterized machines in engineering history. Autonomous rendezvous and docking has been performed in Earth orbit by Russian Progress vehicles, European ATVs, Japanese HTVs, and American commercial cargo spacecraft. Interplanetary navigation is a mature discipline with decades of successful mission experience. Each piece of the puzzle exists. What has not been demonstrated is the integration of all these technologies into a single system that must work reliably on another planet, years from the nearest repair facility, with human lives depending on every link in the chain. Integration is where space missions have historically encountered their most dangerous and least predictable problems. Individual components pass their qualification tests in laboratories. Subsystems perform correctly on test stands. But when all the subsystems are connected into a complete system operating in the actual mission environment, interactions emerge that nobody anticipated. Thermal coupling between adjacent systems causes unexpected temperature excursions. Vibration from one component induces resonance in another. Electromagnetic interference from the power system corrupts guidance data. Software modules that each passed unit testing produce unexpected behaviors when running simultaneously under real-time operational loads. The path forward requires something the space community has historically been reluctant to invest in, because it is expensive, slow, and unglamorous extensive, iterative, uncrewed testing on Mars itself. Not one demonstration mission, not a single proof of concept flight, a sustained program of robotic precursor missions that systematically retires risk across every element of the return chain. Send ISRU plants to Mars and operate them at full scale for years. Observe what degrades. Identify which components fail first. Learn whether the chemistry performs at scale the way the laboratory experiments predict. Send ascent vehicles and launch them robotically from the Martian surface. Instrument them heavily. Record every parameter. See which systems survive the Martian environment and which do not. Send rendezvous systems into Mars orbit and test autonomous docking with the communication delay that real missions will face. See what the guidance algorithms miss. See what the sensors struggle with. Learn, fix, redesign, and send again. This approach is slow. It adds a decade or more to the timeline for a crewed mission. It is expensive. Each Mars landing mission costs billions of dollars. It lacks the drama of a flags and footprints crude mission. It does not generate the iconic images that inspire public support and justify congressional appropriations. It will not make anyone famous. But it is the only responsible way to develop genuine confidence that the return chain will hold when human lives depend on every element of it performing correctly on the first attempt. Some voices in the space community, credible voices with technical expertise and exploration experience, argue for accepting higher risk. Mars will always be dangerous, they say. At some point, you must commit and go. The first crews will face risks comparable to the early polar expeditions of the 19th and early 20th centuries, or the first transatlantic flights of the 1920s. Shackleton, Amundsen, Scott, and Lindbergh did not wait for every risk to be retired before departing. They accepted danger as the price of exploration. This argument has emotional force, and it is not entirely wrong. Exploration has always involved risk. Zero-risk exploration is a contradiction in terms, but there is a meaningful and important difference between accepting risk and accepting near certainty of failure. Ernest Shackleton accepted the risk that his Antarctic expedition might fail. He did not accept the certainty that it would. He prepared meticulously, chose his crew carefully, provisioned his ship thoroughly, and when disaster struck, when the Endurance was crushed by pack ice, he improvised brilliantly to bring every member of his crew home alive. He accepted risk. He did not accept recklessness. A Mars mission that launches crew before ISRU has been validated at scale on the actual Martian surface, before an ascent vehicle has been test-fired from Mars, before autonomous rendezvous has been demonstrated in Mars orbit. That mission is not accepting risk in the Shackleton tradition. It is accepting a probability of failure so high that the distinction between courage and negligence collapses. The psychological dimension of the return problem deserves acknowledgement here at the end of this story, because it reframes everything that has come before. Every public conversation about Mars focuses on the wonder of arrival, the first human footprint pressed into Martian regolith, the first sunset viewed through a helmet visor on an alien world, the sun small and pale, the sky shifting from butterscotch to deep blue at the horizon as the fine dust scatters the fading light. The first words spoken by a human being standing on the surface of another planet, broadcast across tens of millions of miles to a watching civilization. The moment when humanity becomes, for the first time, a species that inhabits more than one world. These are powerful images. They deserve celebration. They represent something genuine and important about the human impulse to explore, to know, to reach beyond the familiar. But for the crew, for the 4 to 6 human beings who will actually stand on that surface, the mission is not about arriving, not really. From the moment their boots touch Martian soil, the clock is running. Every day on the surface is a day closer to the departure window. Every system check on the ascent vehicle is a verdict on whether they will see their families again. Every telemetry update from the ISRU plant is not a science report, it is a survival update. Every morning begins with data review. How much propellant was produced overnight? Is the production rate holding? Are the storage tanks maintaining cryogenic temperatures? Is the ascent vehicle's power system showing any anomalies? These are not abstract engineering questions. They are the daily pulse check of the crew's only lifeline. The wonder of standing on Mars, of seeing Olympus Mons on the horizon, of driving across terrain that no living thing has ever touched, of holding a Martian rock in a gloved hand and knowing you are the first conscious being to examine it. That wonder coexists with a knowledge that no previous explorer has carried. The knowledge that you are farther from home than any human has ever been. That the people who could help you if something goes wrong are separated from you by a communication delay longer than most phone conversations. That your survival depends on machines that have never been tested in this way, in this place, under these conditions. That if those machines fail, no one is coming for you. Not in days, not in weeks, not in months, perhaps not at all. Astronauts are selected in part for their ability to manage this psychological burden. They train for years to maintain cognitive function under stress, to make rational decisions when fear presses toward panic, to compartmentalize existential dread and focus on the next task, the next checklist item, the next system diagnostic. They are extraordinary people, psychologically resilient, technically brilliant, physically fit, and deeply motivated. But no amount of psychological preparation eliminates the fundamental reality. They are on Mars. The only way home is a rocket that must work. And nobody on Earth or Mars can guarantee that it will. The story of Mars exploration, told honestly and completely, is not primarily a story of going somewhere. It is a story of coming back. The going is hard, the coming back is harder. The going has precedent and analogues and decades of robotic preparation. The coming back has none of these things. And until the coming back is solved, not in theoretical studies, not in PowerPoint presentations to review boards, not in conceptual design documents filed in engineering archives, but in tested, validated, flight-proven hardware operating on the actual surface of Mars and returning successfully to Earth, the human exploration of Mars remains a promise rather than a plan. Current NASA architecture documents describe a crewed Mars mission in the late 2030s or 2040s. SpaceX has publicly discussed timelines as aggressive as the late 2020s, though specific target dates have shifted repeatedly, and the company has not publicly demonstrated any Mars return-specific technology beyond the Raptor engine and Starship vehicle. Both organizations acknowledge, in their technical planning documents, if not always in their public communications, that the return problem is the pacing challenge, the single hardest element that determines when a crewed mission transitions from aspiration to feasibility. The engineering community has not identified any fundamental physical barrier to solving the return problem. This is an important statement, and it bears emphasis. The problem does not require new physics. It does not require discovering new materials or new energy sources. It does not require theoretical breakthroughs in any scientific discipline. The Sabatier reaction obeys the same thermodynamic laws on Mars as on Earth. Rocket engines operate on the same principles of Newtonian mechanics regardless of which planet they launch from. Orbital rendezvous follows the same Keplerian equations whether it occurs around Earth or around Mars. Nothing about the return problem is physically impossible. What it requires is engineering. Rigorous, methodical, patient, iterative engineering, on a scale and in an environment that have no precedent in the history of the discipline. It requires building systems that work not just in the controlled conditions of a test facility, but in the uncontrolled, unforgiving conditions of another planet. It requires testing those systems not once but many times, learning from each failure, improving each iteration, and building the kind of operational confidence that only comes from demonstrated success. It requires institutional commitment sustained across decades and political cycles, the willingness to invest billions of dollars in unglamorous preparatory work that may not produce a crewed landing within any single presidential, administration, or congressional budget cycle. Mars is not impossible. It is hard. Specifically, leaving Mars is hard. And the difference between hard and impossible is effort, time, resources, and an unflinching honesty about what remains to be done. Mars is not just hard to reach, it may be even harder to leave. That is the truth that should frame every conversation about human Mars exploration. Not as a reason to abandon the dream is worthy, and the scientific and civilizational rewards of achieving it would be profound, but as a reason to pursue it with the seriousness, the patience, and the rigor that the challenge demands. The first human crew to launch from the surface of Mars, dock with a return vehicle in Mars orbit, execute a trans-Earth injection burn, cross the interplanetary void, and land safely on Earth will have accomplished the single most difficult technical feat in the history of human civilization. Not because of the distance they travelled, not because of the radiation they absorbed, not because of the months they spent in confinement crossing the darkness between two worlds, because they trusted a machine on an alien world to bring them home, a machine built from alien air, powered by alien sunlight or alien atoms, launched from alien soil, and it held. Every valve opened. Every seal held. Every engine fired. Every guidance command executed. Every link in the longest chain ever forged by human engineering carried the load it was designed to carry. When that day comes, if that day comes, it will not be the triumph of boldness alone. Boldness will get crew to Mars. Only preparation will get them home. The triumph will belong to the engineers who tested and failed and tested again, to the program managers who defended budgets for robotic precursor missions that nobody outside the space community noticed, to the materials scientists who characterized seal degradation at Martian temperatures over multi-year simulations, to the chemists who ran Sabatier reactors for 10,000 hours to find the failure modes that appear at hour 9,000, to the software engineers who wrote autonomous rendezvous algorithms and tested them 1,000 times in simulation before testing them once at Mars, to every person who chose to solve the hardest problem rather than announce the easiest victory. That is the Mars return problem. It is real, it is solvable, it is not yet solved, and it is waiting.